In this video, we present our paper about continuous time dynamic graph representation learning. Many real-world scenarios and applications can be abstracted as temporal interaction networks, which consist of a series of temporal interactions between node and arbitrary timestamps. Temporal interaction networks are also known as continuous time dynamic graphs. Dynamic graph representation learning aims to learn time-aware node embeddings by observing some historical events. Specifically, with the network evolving, node embeddings change as well from time to time. Graph neural networks achieved a big success in recent years, but most of them are limited on static settings, which prevent using out-of-the-shelf GNNs to directly model real-world scenarios. Although there are some research focuses on directly learning on dynamic graphs, they have certain limitations, such as relying on discrete relaxation and fail to learn effective inductive biases. On the other hand, temporal events in real-world dynamic graphs occur irregularly, which prevent existing research to explicitly and effectively model temporal clues. To address these limitations, we proposed the NeurTWs walk, which has two bases. Firstly, dynamic graph motifs abstract essential dynamic laws, which are the key in modeling real-world networks. For example, two users are likely to know each other if they have a common friend, as shown in the first figure. Secondly, a dynamic graph motif can have multiple instances, which are temporal walks. For example, two passes in the bottom figure represent the same motif. In this research, we present that it's feasible to characterize a temporal node or an interaction with the surrounding motifs, or we say the dynamic laws. We first introduced the idea of spatial temporal walk, which focuses on three aspects to extract diverse and expressive paths to form motifs after the designed walk anonymization. Then, we introduced how to embed extracted motifs, where we propose two processes. The one called continuous evolution, and another one is instantaneous activation. The first process learns the underlying spatiotemporal dynamics with an ordinary differential equation, and the second process activates the latent trajectories with discrete observations. Finally, we aggregate the embedding of surrounding motifs as the representation of a temporal node or an interaction. To make the model tractable, we first overcome the batching challenge, which allows to calculate the output state of multiple dynamic graph motifs with a single ODE solving, as shown in the figure attached. We then overcome the challenge of large time intervals in real-world scenarios with sample log transformations, which stabilize and ease the solving of continuous evolution process. In a nutshell, our method significantly and constantly outperforms existing methods on dynamic graph learning, which also maintains good interpretability by learning motif-aware representations. Our paper and code are now available with the link attached.